Hello everyone. Today I'm going to talk about pH meter. If it turns red, it's an acid, and if it turns blue, it's an alkali. That's true. Measuring acids and alkalis with litmus paper is something pretty much every one of us enjoys learning in college. It's relatively easy to compare your little strip of wet paper with the colors in a chart and figure out how acidic or alkaline it is. But sometimes that's not accurate for measurement. If you keep your tropical fish, for example, or you're a gardener with specimens that requires soil of a certain acidity or alkalinity, getting things wrong with the litmus risks killing off your prized pets or your plants. That's why it is important to use a meter that can measure pH directly and accurately. So what are pH meters and how do they work? Let's take a closer look. So what is pH? What does its symbol mean? pH is a unit of measure that describes the degree of acidity and basicity of a solution. It is measured on a scale of 0 to 14. The term pH is derived from P, the mathematical symbol for negative logarithm, and H, the chemical symbol for hydrogen. The formal definition of pH is the negative logarithm of hydrogen ion activity. The pH value of a substance is directly related to the ratio of the hydrogen ion and the hydroxyl ion concentrations. If the pH value is less than 7, the hydrogen concentration is greater than hydroxyl ion and the solution is acidic. If the pH value greater than 7, the hydroxyl concentration is greater than the hydrogen ion and the solution is alkaline. If equal amounts of hydrogen and hydroxyl ions are present, the solution is neutral with a pH of 7. Acids and bases have free hydrogen and hydroxyl ions, respectively. The relationship between hydrogen ions and hydroxyl ions in a given solution is constant for a given set of conditions. Either one can be determined by knowing the other. Thus, pH is a measurement of both acidity and alkalinity, even though the definition is a selective measurement of hydrogen ion activity. pH is a logarithmic function. A change of 1 unit of pH represents a tenfold change in hydrogen ion concentration. There are two commonly used methods for the measurement of pH: a colorimetric method, which uses paper test strips impregnated with indicators, and an electrometric method using a glass electrode instrument or the pH method. Fundamentally, a pH measuring system consists of a meter attached to a probe or electrode and a sample solution to be tested. The meter, which can be a moving coil meter, one with a pointer that moves against a scale, or a digital meter, one with a numeric display. There are types of probe: the glass electrode, reference electrode, and combination electrode. Combination electrode is commonly used today that has single combined electrode of both glass electrode and reference component built inside it for simplicity and convenience. pH meter measures the difference in electrical potential between a glass electrode and a reference electrode, and so the pH meter is sometimes referred to as
potentiometric pH meter.
The difference in electrical potential relates to the acidity or pH of a solution. Key parts of a pH meter consist of solution being tested, glass electrode consisting of a thin layer of silica glass containing metal salts, inside which there is a potassium chloride solution and an internal electrode made from silver chloride. Hydrogen ions formed in the test solution interact with the outer surface of the glass. Hydrogen ions formed in the potassium chloride solution interact with the inside surface of the glass. The meter measures the difference in the voltage between the two sides of the glass and converts this potential difference into a pH reading. Reference electrode acts as a baseline or reference for the measurement, or you can think of it simply as completing the circuit. Potassium chloride inside the glass electrode, shown here colored orange, is a neutral solution with a pH of 7, so it contains a certain amount of hydrogen ions. Suppose the unknown solution you're testing, which is the blue color, is much more acidic, so it contains a lot more hydrogen ions. What the glass electrode does is to measure the difference in pH between the orange solution and the blue solution by measuring the difference in the voltages their hydrogen ions produce. Since we know the pH of the orange solution, which is 7, we can figure out the pH of the blue solution. When these electrodes immerse into the blue test solution, some of the hydrogen ions move toward the outer surface of the glass electrode and replace some of the metal ions inside it, while some of the metal ions move from the glass electrode into the blue solution. This ion swapping process is called ion exchange, and it's the key to how a glass electrode works. Ion swapping also takes place on the inside surface of the glass electrode from the orange solution. The two solutions on either side of the glass have different acidity, so a different amount of ion swapping takes place on the two sides of the glass. This creates a different degree of hydrogen ion activity on the two surfaces of the glass, which means a different amount of electrical charge builds up on them. The charge difference means a tiny voltage appears between the two sides of the glass, which produces a difference in voltage between the silver electrode and the reference electrode that shows up as a measurement on the meter. Although the meter is measuring voltage, what the pointer on the scale or digital display actually shows us is a pH measurement. The bigger the difference in voltage between the orange inside and blue, the outside solutions, the bigger the difference in hydrogen ion activity between. If there is more hydrogen ion activity in the blue solution, it's more acidic than the orange solution, and the meter shows this as a lower pH. In the same way, if there is less hydrogen ion activity in the blue solution, the meter shows this as a higher pH or more alkaline. The overall working principle of pH sensor and pH meter depends upon the exchange of ions from sample solution to the inner solution of glass electrode through the glass membrane. The porosity of the glass membrane decreases with the continuous use that decreases the performance of the probe. For pH meters to be accurate, they have to be properly calibrated. The meter is accurately translating voltage measurements into pH measurements, so they usually need testing and adjusting before you start to use them. You calibrate a pH meter by dipping it into buffers or test solutions of known pH and adjust the meter accordingly. Another important consideration is that pH measurements depend on temperature. Some meters have built-in thermometers and automatically correct their own pH measurements as the temperature changes. Those are best if fluctuations in temperature are likely to occur while you're making a number of different measurements. Alternatively, you can correct the pH measurement yourself or allow for it by calibrating your instrument and making pH measurements at broadly the same temperature. Most products require a specific pH for activity or stability, especially in the food and beverage industry, cosmetic industry, and pharmaceutical sector. pH meter is very crucial in agriculture industry for soil evaluation. Major crops require alkaline environment and hence pH meter becomes necessary. It is also used in food industry, especially for dairy products like cheese, curds, yogurts, etc. It becomes mandatory for chemical and pharmaceutical industries. It becomes a significant factor in the production of detergents. Lastly, pH level monitoring is essential in water treatment plants and reverse osmosis water purifiers. You can also calculate pH. To calculate the pH of an aqueous solution, you need to know the concentration of the hydronium ion in moles per liter or its molarity. The pH is then calculated using this expression. pH is equals to negative logarithm of hydronium ion. For calculating the hydronium ion concentration, you can use the reverse mathematical operation employed to find the pH, following this equation. For calculating the pOH, you need to know the concentration of the hydroxide ion in moles per liter or its molarity. The pOH is then calculated using this expression. pOH is equals to negative logarithm of hydroxide ion. For calculating the hydroxide ion concentration from pOH, you can use the reverse mathematical operation employed to find the pOH, following this equation. For calculating the pKa, pKa is calculated using this expression. pKa is equals to negative logarithm of Ka, where Ka is an equilibrium constant for the ionization of acid. For calculating Ka from pKa, you can use the reverse mathematical operation employed to find pKa. For calculating pKb, you can use this expression. pKb is equals to negative logarithm of Kb, where Kb is an equilibrium constant for the ionization of base. For calculating Kb from pKb, you can use the reverse mathematical operation to find pKb using this equation. And now, I'm going to show you a video on how to operate pH meter.
In this video, you will learn how to use a pH meter. pH meters can be small and handheld or larger stationary pH meters. In this video, we will be using a stationary pH meter. The parts of a pH meter include the meter, the arm, and the electrode. The arm allows the electrode to be easily moved up and down into a beaker with a sample to be tested. Prior to use, a pH meter should be calibrated using color-coded buffers of fixed pH. pH 4, 7, and 10 are standard. The first step in using a pH meter is to remove the protective cap from the electrode. The electrodes of the pH meter need to be stored properly, capped and immersed in a stored solution to prevent them from drying out. Next, the electrode must be rinsed using distilled water. Various pH meters will have different procedures for calibration. To calibrate your pH meter, you will need to review the owner's manual for the proper procedure. Begin the process of calibration using the standard with a pH of 7. Once the standard has been calibrated, you will need to remove the sample and rinse the electrode with distilled water. Repeat the process again, this time using the standard with a pH of 4. Once the standard has been calibrated, you will need to remove the sample and again rinse the electrode with distilled water. You will then calibrate the final standard with a pH of 10. When the pH 10 standard has been calibrated, rinse off the electrode with distilled water. pH meters must be calibrated each time to ensure the accuracy of measurements. Using the 3 different pH standards for calibration provides for a wide range of accuracy. You are now ready to measure the pH of an unknown solution. Place the unknown solution beneath the electrode and slowly lower the arm so that the electrode is fully submerged in the solution. This sample has a pH of 5.57 at a temperature of 23.9 degrees Celsius. Once the reading is complete, remove your sample. Once again, rinse the electrode with distilled water. If this is your final sample, replace the protective electrode cap for storage.